Hello, everyone. Today I'm presenting our work named COBRA, a binary transformer accelerator optimized for edge inferences. We combine a hardware-friendly attention mechanism with a true one-bit matrix multiplier engines and a set of system optimizations. On edge FPGAs, our COBRA delivers up to 3.9 teraops of throughput and about 450 gigaops per watt of energy efficiency, achieving over 300 times of energy efficiency over GPU baseline with negligible accuracy loss. I'll walk through the entire design details. So, there are many challenges when deploying transformer module on details on edge devices, but transformers now are powering many tasks like NLP and vision tasks. They demanding a lot of bandwidth, compute memory and bandwidth. Edge devices are everywhere, by the way, but they're ideal for privacy and low latency, which makes on-device inference attractive yet challenging. So in this paper, we focus on accelerated encoder model like BERT, but decoder model like LM will have a separate work. So welcome to check our pages. So how can we bring the real-time transformer inference to edge devices? Yes, we designed an accelerator called COBRA. To develop a transformer on edge devices, quantization is the important and common techniques. So it trades a small accuracy loss for a reduced model size, latency, and memory usage by utilizing low precision weight and activations. Binary transformer is an extreme form of transformer. Quantized transformers. They representing all the weight activations using binary values. It's enable fast execution and low power consumption by the default, ideally. But however, due to the lack of actual hardware support for the design operation, that's usually not the case. So then our solution is that we want to design a actual hardware to be able to support this, and while combining it with the software algorithm level of a code design. So the COBRA key contribution can be separated into three domains. So at hardware level, we propose RBMM, a real one-bit matrix multiplied with the XNOR and plus pop counts, and a novel don't care count mechanism to handle 0 and 1 data paths without breaking the algebra equivalence. At the algorithm level, we develop a shifted softmax, polarized softmax, a hardware-friendly softmax-free attention that output the binary attention score directly. At the system level, we utilize 6-to-3 compressor-based popcorn, quantization-fused MACMOL, and the long bit width of the data packing schemes to unlock throughput and energy efficiency opportunity. So, in binary transformer, matrix multiplication can be element-wide logic operations. We can replace the multiplication with the XNOR plus popcorns. The result is just simply a bit with or logic plus counting on packed vector instead of multipliers. So which is very efficient for customized FPGA accelerator. This figures actually show the high-level architecture of the binary transformer models. We co-design algorithm architecture and hardware architecture to achieve efficient hardware accelerations. We propose hardware-friendly shifted softmax called SPS to replace the regular softmax. And then we propose a real binary matrix multiplication engines, which we will talk about later in the slides. So let's talk about the shifted softmax first. The original softmax used a exponential and produced a symmetrical operation and produced non-binary weights. So the binary model usually compute the original softmax and then binarize the result later on, pay the heavy floating point operation cost. We propose SPS to replace the original softmax and the binarizations with the threshold binary state attention compute that to avoid the floating point operation entirely, deliver extremely high throughput while preserving the high model accuracy as well. So how do we do that? We tune a per head threshold on a small calibration set to align SPS output and the softmax baseline attentions. So this head-wise granularity reflects the diverse role of attention head and give it a good accuracy cost balance while keeping the implementation simple. The SPS threshold search and the model training shown on the bottom right in the figures illustrate our method and the searching strategy of determining SPS threshold. Suppose two attention maps, A1 and A2, are obtained from the same layer I. We define the channel distortion rate CDR as the mean square error between the two maps. The threshold lambda are predefined within the range of 0 and 1 with the search granularity of 0.05. And then the initial value set to 0, which is exactly the regular sign functions. Our objective is to identify the optimal threshold that minimizes the output discrepancy between the original BID model softmax-based attention and our SPS-based attention for given the attention layers. So in this table present our accuracy performance of our binary COBRA models on the glue benchmarks compared to against the original BERT and other binary BERT variants, our model outperformed both of binary BERT and ByteBERT by significant margins, with only about less than 2% of margin minor average performance loss compared to the state-of-the-art BIT models. We call it negligible, and while maintaining provide over 100 times of the potential hardware acceleration advantages, which we'll show on the operation study. Now let's shift our focus to the hardware design side. The COBRA hardware accelerator design, the core component of inside is the RBM engines, or we call it our real binary matrix multiplication engines. Those RBM engines implement a true 1-bit compute for both -1 and 0-1 computation schemes, and how we use it across the whole transformer blocks. So the COBRA have 5 major building blocks: RBMM, layer norm, control, and data packet conversion, and finally a master axis bus interfaces. A single RBMM engine actually serves the majority of the attention computations, including QKB projection, attention, FFN layers. For the RBM modules, we define 5 intrinsic to cover the entire model's computation: M1 for QKB linear projection, M2 for attention score computation, M3 for multi-head attention context output, M4 for attention output projection, and F1 and F2 FFM for FFM projections. We control each mode via the lightweight mode controllers, so the same data path sustains throughput across all the memory. Now let's zoom into the real binary vector dot product modules. We call it RB and VM, which is a core component inside our RBMM engines. As I mentioned earlier, modern binary transformer often use 2 binary computation schemes to boost the information capacity while keeping the both weight and activation binaries. The first schemes compute -1 and 1 by -1 and 1, which is a classic case. So in this case, we compute directly with XML plus pop count. The second scheme output 0-1 by -1 and 1, a mixed sign and unsigned scheme for further improved accuracy. We designed a RBVM engine that as a single compute unit that supports both of the scheme without sacrificing bit level efficiency. So look at the figure on the bottom left. The second scheme, suppose operand A is in -1 and 1. The B is in 0 and 1. After the XNOR, only outcome inside the rectangle are the one we actually care about. The blue rectangle in entries don't care. So basically they can be anything. In other words, the effective truth table reduced to XX 01. This observation led us to keep the hardware fast and simple while correctly handle the mixed binary cases. So here's a trick. We treat those don't care count as a 0. This means in the mixed schemes, we actually we can swap XNOR for the plain AND gate, which is much simpler hardware. But if we simply do that, the pop count will actually subtract the number of zeros because we have more zeros in the entries. So how do we do that? Solve it. We just keep running a count of those extra zeros and add them back at the end to get exact dot product values. The count is kind of easy to get. It is simply the number of zero in the operand B, and we can carry it forward from the previous layers of RBMM since we already compute them anyway. So this works cleanly because the model alternates the 2 binary schemes. The mixed 0-1 and 1 by 0-1 by -1 and 1 cases never appear twice in a row in the model design, so that we can pipeline those correction without any stall. The one more detail is that our XNOR gate is actually built in from the combination of the AND, OR, and NOT gate. So in the mixed cases, we can early out with the AND gate result and reuse the same logic. So the net effect will be the simpler gate, less switching, and the same correct mass. So we implement COBRA in the VITIS HRS, targeting AMD QV260 and ZC102 FPGA board. Both of them are low power edge FPGA board. We use 300 megahertz of clock for final design. The design support BERT-based models. On the ZC102, with the number of P equal to 32, COBRA achieve about 3,900 gigaops at 8.6 watt only, which translates to about 450 gigaops per watt. Compared to the prior works, our design achieved about 3.5 times better throughput and 2.2 times energy efficiency gain over the BAT, which is the previous state of our design. and about 250 to 235 times energy gain over BIT and GPU baseline, depending on the different board. But notably, on edge FPGA, our support even surpassed some of the data center grade FPGA design while using far way less resources and power. So on the same, similarly on this U12 with the number of P equals 32 design, we consume about 122 lookup tables, okay, and 78 DSPs. The layout highlights the RBMM data packing, layer norm, buffer, and control exit buses logic. The data packing units are sizable because they're including lookup table, buffer, transpose path for the vector to data packing conversion, but the overall footprint fits comfortably into our FPGA. To summarize, we propose COBRA, a binary transformer accelerator optimized for edge computing that provide a great efficiency and throughput advantages. Our keynote innovations including a hardware-friendly binary attention mechanism, which calls shifted polarized softmax, SPS in short, a real one-bit binary matrix multiplication engine, RBMM, and thirdly, a adaptive computation flow for binarized transformer models. Finally, we would like to acknowledge our sponsor, NSF, AMD, and UCI Assembly School of Engineering. Thank you guys very much. And if you have any questions, please feel free to contact us or contact Professor Sudao Huang. Thank you.